theorem. This is follows from the definition of normal subgroup. Every subgroup of an abelian group is a normal subgroup of G. Every subgroup of an abelian group G, abelian group G is a normal subgroup of G. Before the proof, we consider the illustration. Z6 is consist element 0, 1, 2, 3, 4, 5. Here we taking the subset from Z6 0, 2, 4. This is a subset from Z6 because of there are possibilities of the subsets containing the elements 3 or 2 because of the Lagrange's theorem says that the relation between number of elements in the group, number of cosets in the group, and also number of element in the sets. So there is only possibility 0 to 4. Suppose if it is the theorem, Lagrange's theorem says that cardinality of the group divided by the number of elements in this subgroup equal to the number of cosets of H, the index of H. This is index of H. Suppose here there are 6 elements. Number of elements in the sets is 3. This is equal to 2. There are 2 distinct cosets. That means that the index of H is 2, or you can write like this: G order of the group, index of the subgroup, number of elements, cardinality of the subgroup. This means here 6, index is 2, number of elements in the sets, cardinality of the subgroup H is 3. So this is a subgroup of consisting 3 elements. We will find the left coset. Suppose under the modular addition 6, suppose we have to taking element 0 from Z6. This is H and also right cosets. Suppose you have find out the left cosets from the element 1. We have find 1, 6, 8, 6, 0, 1 under modular addition 6, 2, 1, under modulo addition 6 4. This means 1 3 5, and also right cosets. H under modulo addition 6 1, under modulo addition 6, under modulo addition 6, under modulo addition 6 1. This is 1 3 5. Here the left coset equal to right cosets. So H is a normal subgroup. This is normal. H is a normal subgroup. H is a normal subgroup. Not only here, you take any subgroup from the abelian group, which is a normal subgroup, which is the theorem. You have to prove the theorem. In general, proof. Let's G be an abelian group, G be an abelian group, and H be a subgroup of G. Let's A belongs to G. We have to prove that. We have to prove that AH equal to HA. This is enough to prove that AH equal to HA because of the definition of normal subgroup staying sets. For any A belongs to G, AH equal to HA, H become a normal subgroup. Let's X belongs to AH, then we can write X is AH for some H belongs to H. This means here X can be written as HA because of G is an abelian group here. G means Z6 is abelian group. Every element of the form here A, H, A, H. Here you watch H, A. This become 1. This is also become 1. These two elements belongs to Z6. So every element can be written as AH or HA. So X belongs to X can be written as X equal to HA, since G is an abelian group. G is an abelian group. So here X belongs to HA. This is an element HA, so this X belongs to HA. The element X belongs to AH, which is also belongs to HA. It can be in generalized. Every X belongs to AH, which is also an element of HA. This means that AH is contained or equal to HA. Every element of AH is also an element of HA. Here every element of AH is also an element of HA. So therefore AH is contained or equal to HA. Similarly, we can prove that HA is also contained or equal to AH. Therefore HA equal to AH. This leads thus H is an abelian, H is an normal subgroup of the abelian group of an abelian group G.